Hello, everybody. Thanks for tuning in, and it makes our day. And to be very frank with you, there are hundreds and hundreds of concepts which goes behind when we are building a neural network. Neural network from scratch, from a vanilla Python perspective, is not the biggest deal that you can really do. But when you have a TensorFlow, a PyTorch as an abstraction, and now you're just going ahead and now trying to build on something new, that's going to have a lot of impact. And over a course of time, I think knowledge distillation is one of the concepts which has been underlooked, but it's very important in research. Of course, we'll be going deep in this session over a course of time. During the month of March, I've been planning to do a lot of sessions on it. So we'll be coming out with a lot of sessions. So make sure that you learn whatever it is being taught here and just take this as a prerequisite. Of course, a lot of prerequisite sessions and everything will be happening, but stay tuned for the future sessions, and I hope Madam is always jacked up for the community work and she's always ready to deliver the talk there. And thank you so much, ma'am, for being on the show. Means a lot to us.
Thank you. Thanks a lot, Vishwas, and thanks a lot for inviting me for the session. Yeah, I think let's go for the session. It's fine.
Sure, sure. Perfect.
Okay. Yeah. I mean, sorry for the background, but I think it should be fine.
Yeah.
Yeah. Let's go to the session. Before going to the session, I'm Sri Ranjani Ramakrishnan, a Google developer expert in machine learning, and I have also, been in this machine learning community as well as research for a couple of years. So let us go for the session. So in today's session, we are going to talk about knowledge distillation. I hope my camera is fine because it just got frozen here for me.
We were able to see you.
Okay, fine.
Yeah.
Now I think it should be fine. Yeah. Okay. So yeah, let us go to the knowledge distillation topic. So before going to the knowledge distillation, let us try to understand where it came from and why it is important, because I think those questions are very important to answer before. Excuse me. Hello. Sorry for the confusion. Hello.
Now your screen is frozen, and
Is it better?
yeah. I mean, we can't see your shared screen.
Yeah, just a minute. There was this technical glitch, and I'm really sorry about it. Yeah, it's better. Yeah. Okay.
Yeah, it is.
Okay. So yeah. So today we are just going to see the overview of knowledge distillation. I'm not going to go in deep about all those equations and stuff, but to get an overview of the whole topic. And I also want people to take it as an opportunity to try out knowledge distillation, because it's really awesome, and it has a lot of potential to get extended and being used in a lot of real world applications. So where it all started? So it all started with the concept of model compression. So we know that with this deep learning era, where we use deep learning in each and every small devices and everything around us, it's good that we have a state of the art accurate models, which are very big, because it has its own importance and the need to solve some problems. So for example, if you take T5, which is like 11 billion parameters, and GPT-3 is like 175 billion, and we just increase in those size of the parameters. But there is also a side effect, or there is no free lunch with respect to building these models, that the carbon footprint of such models is like quite enormous. And if you compare it with even a US car, including fuel for average one lifetime, you can see how much big it is even with a normal transformer model. So what does it tries to tell us is that this is not, it's one of the best solutions, but it's not always the a solution which is usable in every case. So what we can okay, I think some issue with the camera. I'll just freeze it, and let me try to focus on the slide. You can also have this resource constrained environment where we move towards edge devices, but there are a lot of resource constraints in terms of memory, latency, power consumption, bandwidth, privacy, etc. So what actually happens is that we need a model which is compact, which works in such resource constrained environment, and also it's very efficient, right? So that is the need. And we can see that model compression is a technique where you try to reduce a over parameterized model to a smaller model. And so there are common techniques of the model compression are pruning, quantization, matrix decomposition, knowledge distillation. By using these techniques, our goal is to achieve, a smaller memory footprint model, and it leads to faster inference time, which can be deployable and like which is very efficient also, right? So that is kind of the aim what we are looking at. So to go a gist of what are these common techniques. So pruning, they try to reduce the architecture of the neural network through reducing the layers or the neurons and stuff like that. And then quantization, you try to go from a higher precision to a low precision model without much loss of significance, performance difference. Then matrix decomposition is that you use linear algebra matrix decomposition techniques to factor the weight matrix of the learned neural network into different latent factors, and then use that reduced factored model for the final training and inference. So technique like singular value decomposition can be used for this. Then today we are going to see about knowledge distillation, where I will be explaining what knowledge distillation is and why and how it started. So we generally have seen that compared to a model which you have trained, we always have ensemble models giving us better performance, right? So why ensemble models give us better performance is because compared to the learning of one function, if you try to make a combination of a function, which always gives better performance. But the issue with the ensemble model is that they cannot be trained, because multiple versions of it has to be trained, and then you have to ensemble it, and they cannot be computationally efficient in every case. So they are usually expensive based on the model architecture. Busilwa and their collaborators, they thought that, okay, let us go for this concept of model compression, where they thought, it is good to transfer the knowledge learned from the ensemble function into a smaller model, and thereby they are able to transfer the knowledge, as well as the smaller model is more efficient, which can be used in real world systems. So Hinton, he publicized this method, and it is called distillation, and he used soft logic, but that is also transfer of knowledge. He inspired from Usilia, and then he tried to use some other method of transfer, but the concept is the same. So, what is knowledge distillation? Knowledge distillation is a procedure where the knowledge is transferred from the teacher model to the student model without a significant loss of performance. So, we can see that there are a couple of concepts here. Like one is a teacher model, one is a student model. Okay, what is a distillation? How do you do the transfer, etc., which I'll be explaining in multiple slides. But what is knowledge distillation? The whole procedure where you want to transfer the knowledge which is present in the teacher as a function, and that to the student without much significant loss of performance. Okay, so I just take a pause here to see how you can just get what knowledge distillation is. And now, so how it is done. So now we know that this is knowledge distillation, but how it is done. So we can take new teacher as well as student models from the same or a different architecture, and you need a, of course you need a loss function to optimize based on, right? And we know that we want to match the student to almost is equal to the teacher, so we need a optimizing function which is going to mimic the teacher, and that is done by matching the softened logics of the teacher model and the general cross entropy labels. I'll try to explain the concept again, but yeah, how do you generally soften the logic? So you try to soften the logic by temperature scaling function and the softmax function. So what does it mean? So generally you have a neural network, you try to get some feature representation, and then you apply a linear classifier layer, and then at the end of the layer you are going to get a logits, right? So after getting the logits, you will be applying a softmax function to get into a class probabilities to be mapped to different class labels. So they are saying that this softmax function can be softened instead of mapping to a hard label which is 0 or 1, and so that the whole function becomes more smoothed, but it yet reveals the difference between the classes. So that is their idea, and they say that by doing this, you have some dark knowledge which is present in the teacher function, which gets which can be utilized to be transferred to the student. So that is the major idea of this vanilla version of the knowledge distillation. So let us see this say for example, if you're going to combine or ensemble model, then what do? You try to take the different models, you combine the class probabilities, and you try to combine using average or sum or geometric average, whatever the way of combining the statistics. And when you try to do this, you can see what happens when you do a softening of it. So we know that this is the one hot label encoding for excuse me, for different classes here. And so now I know that the particular example it belong to class dog, so you have a 1 there. And this is the output of this geometric ensemble of the probabilities. Now you say that okay, so dog has 0.9 probability and cat has 0.1. These two are like very very minimal, but you can see that it's very peaky, because you try to match it to this hard target labels, right? But this might still not give us the correct information with respect to the knowledge of the function. But when you try to soften it, that is scale it by a factor of t, the raw logics, you can see how it happens when you try to soften the output of the ensemble, right? You still get the highest class probability for dog only, but then you have the smoothing of the value, so the probabilities gets distributed much better. So these softened outputs actually reveal the dark knowledge in the ensemble. We call it dark because we cannot interpret what is the knowledge, but we can see that it is having the teacher's efficient knowledge which is present in the which can be transferred to the student. Okay, so in terms of equation or the loss functions, what you try to do is that you are going to have, so we know the normal softmax function is this, that if this is the raw logits which you will get from a particular class, you are just going to get exponential of zi by sum across all the other logits, right? So this is going to be my softmax function. But in this case, because we want to smoothen it out, we are going to put a scaling value of T, and this is called a temperature parameter. And this temperature parameter tries to smoothen out. So for a hard output of 0 or 1, this is going to be 1. But if you want to soften it, then you want this value to be greater than 1. So what we try to do is we are going to have two different loss functions, which is like one which is going to be for hard labels, and that is the general cross entropy loss functions, where you try to get the hard targets. The other one is going to be the soft target functions, which is by using this t value, which is greater than 1. So this loss, which is called as the distillation loss, you try to mimic the teacher's targets, and this loss is called as the student loss, with it's a general cross entropy loss with it. And so the total loss of the knowledge distillation is going to be the weighted sum of this student loss as well as the distillation loss. Generally you give less weight for the student loss compared to the distillation loss, because you want the distillation loss to have more importance, but also you don't want to miss out on the student loss information. So that's how it is. Now, pictorially, you can see that you pass input and you have a teacher model. So it can be any teacher model, it can be any student model, and you just get the logits here. So generally you get the logits here before applying to the softmax, and so this is the softmax you apply. So here you can see that at t is equal to 1, you are trying to map using the hard label, which is the ground truth label, and this is the loss function. So which you call it as a hard prediction. And then when t is equal to t, which is greater than 1, you're going to have the soft labels, where you try to match or mimic the class predictions of the teacher model, and then you try to making it as a soft labels, and then you get the distillation loss function. So that is how the general knowledge distillation works. So we have the student loss and we have the distillation loss, whose weighted sum you're going to optimize on for the complete training. So with respect to the procedure, we can see that you have to train the teacher model to get the teacher logits, which is the soft labels, and then you have to train the student model, to get the student logits, which is the soft predictions, and then you find the student loss using the hard label and soft predictions, and distillation loss using soft prediction, soft limit, and then you minimize it here. Okay. So before going to the variants, I hope I'm just taking a pause here to make you understand this concept of knowledge distillation. So knowledge distillation generally, was introduced with this vanilla version by Hinton, and after that there was an explosion of works which is based on knowledge distillation itself, which is like quite huge. Covering different variety and concepts of knowledge distillation. So here, I want to point out that the major three, components of this knowledge distillation is as the two main words, knowledge, and then distillation, and then the architecture of the student as well as the teacher. So what is the knowledge here? We call the knowledge which we, or the function which we learn from the teacher after the softmax, is the knowledge we have. And distillation is like, how do you distill the knowledge from the teacher to the student? So you have multiple strategies for it. And then you have different types of architectures which call it student, and how different architectures can be considered, and then the ways of considering the knowledge distillation scenario itself, right? So because here you considered it for model compression, but it's not necessarily that the knowledge has to be distilled only for the case of a model compression. So let us get some variants of knowledge distillation. So the first one is like the different types of knowledge. So one is a response-based knowledge. Like you can see from this overview diagram that this whole thing is a teacher model, and you are getting output from the response of the teacher. So it's basically from the output layer of the predictions, and which is based on soft targets. So those you want to mimic to the student. So this is called as the response-based knowledge which you want to transfer, so that there are works which is based on that. Then you have feature based knowledge. So you call feature based knowledge is that you mimic the feature maps from the intermediate layers, and you try to basically you say that okay, only the features are actually discriminating and learning the discriminatory information between classes. So why can't we take the intermediate layers and the feature maps, and then you try to distill that to the student? So so here we will just apply the transformation function where you have the feature maps which is not in same shape uh, as the student. Then you try to apply some transformation function. Otherwise you just directly take the intermediate layer feature map and try to use the distillation loss to go towards the student. So that is the feature based function. So for matching the different feature maps, you can use any similarity based functions like KL divergence or L2. I mean, like it could be anything. Then you have relation based knowledge. So what does it mean by relation based knowledge? So I just want to find the relation between the input, hidden learned layers as well as the output. So what you try to do is that why not get the relations instead of directly the feature maps or data samples. So that is based on try to learn or model the correlation between the teacher and the student feature maps or any other correlation based functions kind of thing, so that to capture the relations. So that is called as the relation based knowledge systems. So this is the variations you see in terms of different types of knowledge. Let us go to the next for distillation. So the distillation strategy, like you actually train the distillation using different types of distillation. So one is offline distillation, the other is online distillation, the other is self distillation. So in offline distillation, you generally have a big pre-trained teacher model from which you want to distill the knowledge to the student, and it usually happens offline as the name indicate. So here you can have a teacher which is like very big and then try to put the student. In online distillation, you want the teacher and the student to learn, mean to be updated as an end-to-end architecture, and always we might not have a pre-trained model available in every scenario. So going for online distillation has its own advantages. Then you have self distillation. So it's a special case of online distillation. You just say that okay, why can't I have the teacher as well as the student the same model, and you try to distill itself within its sub networks. So that is the self distillation part, where you try to optimize on the distillation loss within its own sub networks. Right? So these are the different ways of distilling the knowledge which is available in the literature, I mean, currently. The other thought process is that model capacity gap, which is between the teacher and the student architecture, is very important. So if I say that only if my teacher is going to be very efficient or it's like be trained to its capacity, then we say that a student can be also be made as close as possible to the teacher. So we want the capacity of the student and teacher to match. So the gap between the model capacity can be reduced using efficient architectures. So you can have different student architectures, like a shallower version of the teacher, like you try to remove some layers or neurons from the teacher and then make it as a student, or you can have a quantized version of a teacher, like you have a teacher which is 32-bit precision, and then you try to reduce it as an 8-bit for a student kind of thing, and then you have the same model as a teacher and then see how you can distill it. And so it's not necessary that the student has to be always smaller or shallower than the teacher, but it can have almost equal parameters as the teacher. But the like what you want to distill and what is the knowledge and how you want to do this, so those try to vary for different types of knowledge distillation setups. So I mean, this is one example where apart from model compression, which we are seeing till now, so you also have the teacher which is trained on a clean data. So you like, why can't I have a clean data and then go for a student to train on the noisy data and get it to be learned like the teacher. So that is more a difficult task for a student, but that's also a knowledge distillation. So it's not necessarily in the setup of model compression, right? So that is what we see. So here in this particular case, your student as well as the teacher are going to be in the same architecture, like almost at the same capacity as this, because the task is going to be different here. So yeah, so that is about the different architectures. Now, the next is different scenarios. What are the different scenarios of having knowledge distillation setup? So one is going to be multiple teachers. So when I say multiple teachers, like why should I learn only from a single teacher? So I can have multiple teachers from which you can just learn from. So what you try to do in that case is that you try to get the information from multiple teacher. You try to ensemble them, or you also take their intermediate layer information together, put it together, and try to get the final distillation loss. So people have also done on having a teacher assistant kind of thing set up also. Then something called cross modal. This is mostly towards having multiple cross modality setups, like this teacher is trained on a, single modality, but student is trained on a completely different modality, and you should have a pairwise matching of the information between the data. But otherwise, if it's not, then how do you try to distill from one modality to other? So that is the concepts for cross modality. Data free distillation works. So in data free distillation works, they try to have issue of security or privacy because you don't have access to the teacher's data, model cut data. So what you try to do is you try to get the feature parameters, and then try to reconstruct the data of the teacher, and use that model to compare and get it from compare with the student to get the distillation. So that is kind of setup. And adversarial uses adversarial losses, like having a discriminator generator, and see whether you can discriminate between the student and the teacher and get the logits or the feature map. So that's one way, but there are also other ways in the adversarial distillation setup. So graph-based is mostly try to model the vertex as some self-supervised teacher, and then try to get the information from it. Attention-based, you try to map the attentions of multiple of the teacher and the student model, and then based on the optimization using that function. So quantized is mostly like from a higher quantized version for the teacher, go back to a lower quantized version as student model, and then try to do distillation. So basically, these are some clusters of grouping of the works of knowledge distillation. But there, of course, there are so many other works which, of course, I've not covered in this talk. But we can see how and where the knowledge distillation has grown exponentially, because we saw that from a normal vanilla setup of having a distillation, people have tried multiple different cases based on knowledge architecture, and then based on the distillation setups, and also other kind of scenarios where the knowledge distillation can be used. So I mean, you can also try from your problem settings, what you are working on, see if knowledge distillation or the concepts can be applied there, and maybe you can also come up with a multiple concepts for knowledge distillation in any of the scenarios, or a new one. So that is all about the concepts or the theories, or for the knowledge distillation which I had today. So let us go to a collab notebook and see how the model can be trained on. So let me stop sharing, and then let me share the collab notebook.
Yes, ma'am. I think they will take care of the share screen right now. And yeah,
Yeah, 1 minute. I'll just share the screen.
sure, sure, sure. Take your time.
Okay.
Sure.
Can you see the notebook?
Wait, ma'am. Yes, we can see the notebook. Yes.
Okay, yeah. So yeah, I have mentioned PyTorch, but let us see an example in TensorFlow first, and then see. So this is like the notebook written by Kenneth Bob, and he just wrote in Keras also the implementation. So I thought that it will be easy for you all to go and check also. So yeah, so what we try to do is generally first you import the necessary libraries. So you have the TensorFlow, Keras, and NumPy, etc. Basically, as I mentioned earlier, like you're going to have multiple steps. Like you first train the teacher model, and then you're going to have a student model to train, and you just get the student loss function, and then you have a distillation loss function. Then you have the weighting value between the student as well as the distillation loss, and you have the optimizer. What is the metrics to evaluate the performance, right? So these are the steps we are just going to follow here. So let's construct first the distiller class itself. So you are define the distiller based on the Keras model, and you're just going to have the teacher as well as the student model. So here he tries to compile all the needed parameters like optimizer, what are the metrics you want to evaluate, the student loss function. So you pass on all the values, and what we do in the train step is that you just get the data, unpack the image. I mean, here he has given an image on MNIST, so you can just get the image and the label. So basically, you first do a forward passing of the teacher, and we don't want the teacher to be trained here because you're going to take it from pre-trained. So then you just take the training as false here, and what you will get at the end of the day is the predictions from the teacher, right? Then you are going to get the student. Okay. Uh, um, is it okay? I think it's big enough. So yeah. So what we try to do is that let us first define the whole class as a distiller class, where you are going to pass the teacher and the student models, and you're going to compile all the parameters like optimizer, what is the metric which you're going to measure the performance on, what is the student loss function, distillation loss function, what are the weighting values, and the temperature. Okay. So here, after getting that, you're going to define the train step. So here we use MNIST information. So MNIST contains multiple images with the digits. So here you're going to have X and Y, which is the image as well as the label, and you're going to predict. So first step is you want to just pass on the data to the teacher model, but then you don't want it to be trained, so you just put training as false. You get the teacher predictions, and we know that we want the student predictions. So you just forward pass the student, but then you want the training to true. So you get the student predictions. Basically, after getting the student predictions, we want the student loss to evaluate on the hard labels and the student predictions. So that is the student loss, as I explained earlier. And here is this distillation loss, which is based on the teacher predictions. Like you apply softmax with teacher predictions with softened by the temperature value. Similarly for the student also. Now once you get the distillation loss, my total loss is going to be alpha times student loss plus 1 minus alpha times distillation loss. So this is the total loss which I'm going to optimize on. So here you're going to train basically every step, and you are applying the gradients and get the values and stuff. So these steps are basically going to update the weights, and this is going to see what, like, you have to update the metrics in whichever he has compiled. So you are just updating the state, and finally get the student as well as the distillation loss. So this is going to be the train step. Now in test step, what we want is we just want to forward pass, calculate the loss, right? So you just give the student, and you don't want the training to happen. So you just get the Y prediction, and then you are going to have you're going to compare with the hard labels and the Y predictions. So that is going to be my final loss, right? So this is going to be the you update the metrics based on that. So that's about the test step. So creating so that this whole thing is about the distillation class. Now the teacher and the student can be any model. So here in this case, he has put the teacher as a model with convolution, ReLU, max pooling, convolution, and flattened and dense. So this is going to be the teacher model, and which is with 256, right? So here it is going to be 16. So that's the a shallower or a smaller model of this. And here also you can just see it's a 32. So this is this is going to be a bigger teacher model, and this is going to be a smaller student model. But of course you can have any architecture here. So you can even have a pre-trained model for the teacher, and you can have any other model which you are defining as a student, or like both pre-trained models with a reduced version, etc. Anything can be based. So it's model agnostic of this distillation setup. So yeah. Now, so when you try to, I'll just explain later. So now what you try to do is that, yes, as I mentioned earlier, so you're going to have the MNIST data set. I think TensorFlow has this, or Keras has this data sets directly where you can just get it loaded. So you're going to get the MNIST and directly load the data set. So when you try to load it, you're going to get the train values and test values directly, and then you want to normalize, of course. So you try to normalize and reshape the data, and once you've done it, what you will be, so MNIST is going to be like the lower version of the data with less channels. It can be easily trained here. So that example here is taken. Now you have like basically what you do is, the first step is that after defining the model structure, you are going to train the teacher in a usual manner. So you try to give the loss optimizer and the metrics. So basically here he has given Adam, which tries to adaptively change the learning rate, and you can give SGD or any other optimizer technique. And loss is going to be sparse categorical. Why? Because you want it to be the cross entropy loss with heart, and then you have the metrics, which is the accuracy based on that, right? So that is going to be your teacher model. So you're going to fit it, and you're going to evaluate the model. So you can see how the teacher model is performing, right? So it's already 97.59 accuracy. Now, this is like just training the teacher within this. Now, what we try to do is that we want to distill the teacher to the student. So this knowledge has to be passed on to the student, and for that we are going to use the distiller class, which we have defined already. So where we are going to pass the student as well as the teacher, and here also you're going to compile using the Adam, and the metrics as sparse categorical with the cross entropy, and yeah, this is so student loss function is also the same, sparse categorical, and for distillation loss we want to compare two functions, right? So for that you're just going to give it as a, KL divergence. Yeah, so that we have to give for that. And then alpha, which is the weight value, they have given it as zero point 0.1, but yeah, according, as I said, that distillation loss has to be more weighted, more compared to the student loss. So accordingly you can give the set of the alpha, and temperature they have given 10. After passing on the distiller and the student, you are going to fit the class model by the same thing, and then you can evaluate the model on the test data. So we can see here, already 97, right? So here it's also 97.59, which is approximately, similar thing, which you're going to get by distillation, right? With much reduced model parameters. And you can also train student from scratch, right? So usually when you want to compare, you want to compare the trained student model ka performance, trained sorry teacher model ka performance, and then distilled distilled student has to perform as equal to the teacher, and you want to know how was the raw student performance. So that is this, you want to train this student from scratch. It's the same setup. You are just giving the trained student, and here again you can see it is 97.85. But so in this example, you don't find much difference with respect to the performances, but actually the reduction of the number of parameters in the models with respect to the performance is quite huge, seen in multiple different scenarios. But this whole notebook is just a very basic version of the knowledge distillation. You can see that you can try with different seed values, and try with different architectures and stuff to get the digital student to be as close as to the teacher, right? So that's what we have to see. And most of the cases, a teacher will be much higher compared to the student trained from scratch, but in this case it's a smaller data set example, so it is coming around, everything is around 97, 98. But then usually the teacher will be like around 70, 70 and all, and this will be like around no so this will be around 90s, this will be around 80s to 70s. So that how the difference will be there, and the digital student will almost match the teacher. So yeah, this is one such notebook with which is explained with tens of few. Um, just a minute. Yeah, I
Sure.
can. mm, if you
You can
want, I
share it in
have.
the.
Sorry.
You can share the notebook as well. Like, yeah, we can.
Yeah. Okay. Yeah, I'll share. I mean, this is the link is available. I'll just anyway share the link of the notebook for
Sure, sure.
reference. Yeah. Okay. Yeah. So that's all I have with respect to the concepts,
Knowledge
but
distillation.
yeah. So yeah, so that's all I have today with respect to the concept. So these are my references. If people interested can study this main paper, model compression, and these are some of the
Sure, you
tools.
can share that in the private chat, and we'll put it in the public
Yeah,
chat.
sure. Yeah. So that's it from me today. So
Yeah, and also like, ma'am, like I just wanted to know, like, how are these abstraction affecting, like, in terms of we are talking in terms of secure ML, we are also talking in terms of fairness in the ML today. So how is it being architected today? And also, how is knowledge distillation helping us understand all this?
So knowledge distillation help us, as I mentioned that in one of the scenarios, right? Like you have the concept of data-free distillation, right? So where you're just going to have, you don't have the availability of data from the teacher or the model parameters. So how are you going to utilize the learned latent representation in between to use and distill knowledge from. So basically, you try to match the feature layers directly between the learned teacher and the student. So in that way, you have the privacy being preserved. You don't have the actual information. Everything is going to be put in the latent representation space, right? So then also you're going to distill the knowledge. So that is one thing. There are the other. That's one way to answer like your question on how the setting is being done. Mostly, I think now data-free
Yeah.
distillation is one of the hot topic of how it's been done. Yeah.
Sure, sure. I think that's perfect. That's perfect. And thank you so much, ma'am, for taking this session. Means a lot to us. And of course, like a lot of people, it was so in detail. Like, many people were saying it was so good. She's explaining in a lot of detail. And we are like, okay, fine. If you guys are enjoying, that's actually more than enough for us. So thank you
Okay.
so much, ma'am.
Thank you. Thanks a lot. Yeah, thanks a lot for providing me the opportunity, and you can always, connect with me in my social media links. And yeah, happy learning.
Yeah, ma'am. Thank you so much.
Thank
I
you.
think we can end the broadcast.